what we'll be seeing in the 2 days lecture. So for the 2 days lecture, we'll be for the 2 days lecture, we'll be seeing the single source shortest path algorithm again. We saw single source shortest path algorithm few lectures back, right? And we saw that there is a data race in that code, and in the 2 days lecture, we'll see how to remove that data race. Then we'll start with a new instruction, which is atomicCAS, and we'll see and we'll learn that how to use that atomicCAS, and we'll also see how to implement blocks and single sections using atomicCAS. Then we'll see few more examples of the atomicCAS, and and then we'll start with the barriers. We'll formally define what the barriers are, and we'll see few of the examples related to the barriers, and we'll see few more important points pertaining to the barriers, and probably there will be stopping for the 2 days lecture. So with this, let's get started. But before, quickly let me look to the chat. Okay, so there is no issue with the audio right now. Is that what I'm assuming? In case there is any issue, then please do let me know so that I can get to know that get to know what should be done. Okay, so with this, let's get started. So this was the last slide that we saw, right? So in the previous lecture, this was the last slide that we saw, and we saw that we have this kernel D kernel in which we are incrementing this variable x, and we were incrementing this variable, and multiple threads. If you see, this kernel will be executed simultaneously by multiple threads, and there is a chance, since this x++ at the assembly level is broken into 3 instructions, there is chance that multiple threads so there is a chance that this multiple threads execution of this kernel by multiple threads might lead to a data race. And in order to avoid that, we saw that we need to use something called as atomic increment to ensure that all or none behavior. And then we also saw later that if we launch the kernel using k1 into k2, which is as a k1 into k2, that is k1 into k2 threads, then it would ensure that this variable x is incremented exactly k1 into k2 time, irrespective of what is the execution order by the multiple threads. So and when this effect will be visible, this final result, which will be k1 into k2, which is stored in the variable x, will be visible after this kernel has finished its execution. Okay, so that is a brief recap about the last slide of the previous lecture. With this, let's move on further. So again, let's come to this single source shortest path algorithm. So again, as a recap, if you remember that we were interested in computing the shortest path from the center of India, which is Nagpur, to every other cities, and we assume that we are given the GPU graph library to read the graph and performing traversing through the neighbors and all those things. Assuming that thing, and assuming that each node operates on its neighbors, we wanted to find the shortest distance from the center of India to all other cities in the India. So this is the sort of a typical graph that we will have. That is, this vertices are the cities, and the edges represent the distance between the cities. And we also wrote the code corresponding to it, if you remember. So this was the code corresponding to it, and we saw that there is issue with this code, right? And what was the issue with this code? That the distance to C is computed wrongly. And why this happens? This is because this reading of distance and writing of the distance here can be done by 2 threads in an independent manner. So it might happen that vertex A and vertex T will read the vertex of the will read the distance of the vertex C, which is infinite because initially everything is every distance is every distance of every node is initialized as infinity except the source node. So distance of A is 0 except that all other have distance infinity. So C has distance infinity. Now what A and D will do is A and D will read the shortest distance to C, which is infinite here, And then since both of them both of them know that the distance to C, current distance to C is infinity, both of them will try to update the distance of C using this instruction. And what will happen is A will try to update it to 3 and D will try to update it to 4 plus weight of this edge, which might be 2. So 4 plus 2, which is 6. So in that case, the last thread, the last one to update will be the final distance of C. So it might happen that final distance to C might be 6, and that is wrong, right? Because the shortest distance is 3, and yeah, so we might get the wrong shortest distance here, and that is because we are there is a data race between reading and writing here. And now I would like you people to think that how can we remove this data race by using the atomic instruction. So please think about it. We have this code which is racy. We know that it has the data race, and we also know that the data race is here, which is causing the correctness issue. The data race which is causing correctness issue is here, and we want to fix this code. How can we fix this code? Please think about it and post your answers in the chat. And meanwhile, if you have any questions, then you can also ask related to this code if you have some issues related to it in the lecture the lecture where we discuss this code. Okay, quickly moving to the chat if there is some. Okay, thanks for confirming that audio is fine. Yeah, so again, apart from that, there is nothing. Okay. Uh, hmm. Okay, so again, question is that this code is racy, and data race is occurring here, which is causing the correctness issues, right? And if we want to modify this code such that data race is removed, and yeah, precisely this thing should be modified. This part should be modified such that data race doesn't occur, and we get the correct distance to nodes such as C, and there might be multiple nodes like C in the graph. So I'll wait here for a few seconds to for you people to think, and then we'll start discussing it. Okay, there's no response. Let me go back to the slide. Wait for. I'll wait here for a few more seconds. Yeah, for you people to try out. Yes, is there any suggestion? Probably I missed it, but yeah, can you please speak out loud so that okay, there is some suggestion in the chat. Rishikesh is saying we can apply mutual exclusion for the if block using lock and unlock. Okay, so that is a correct suggestion, I would say, but is there anything else we can use? Can we use atomics here? Can we use atomics, or the mutual exclusion is one of the way? That is correct. The chat. I guess there is some noise from someone's side. Just a moment. I request you to everyone to mute unless you have any questions. If you want to discuss any aspect related to this slide, then please unmute yourself and ask. Else, please mute yourself. So there is. Okay, if you have any questions, then you can unmute yourself and ask. And yeah, but let's move on further from here. So yeah, one of the way in which we can ensure that there will be no data errors is to uh, place lock here before entering the if condition, and then after exiting the if condition we can use unlock. But the another way is to use atomics. And how can we use atomics here? So for that we need to see what kind of operation we are doing. So essentially, if you see, the operation that we are doing here is finding the minimum, right? So we are checking if the alternate distance is less than the current distance of any particular node, right? Or current distance of a neighbor of a particular node. We are checking if that alternate distance is less. Then what we are doing is we are updating that alternate distance, and that is exactly what is the minimum operation, right? So we are interested in checking if the alternate distance is less than the distance which is present in this dist of n, and if that is the case, then we update the dist of n. And for doing that, CUDA provides us the very nice this atomic instruction, which is atomicMin. And using this atomic instruction, we'll be able to exactly do this thing. And yeah, and the crucial point here is that this thing, which is checking the distance, whether it is less than the alternate distance or not, and then setting the distance to the alternate distance. If it is less, everything, this entire thing is done atomically. So no other thread will be able to execute this two statement if some thread is executing any of these two statements. And that is exactly what we want, right? We want this reading and writing to happen atomically, and hence this atomicMin exactly serves our purpose here. And hence replacing these two lines with just this atomicMin operation uh, will help us ensure that there won't be any data errors. So actually the correct code is this, by removing this if condition and placing this atomicMin. I hope that this is clear. In case you have any questions here at this slide, then please unmute yourself or type your queries in the chat.
Sir, can you explain that atomic min statement once?
Yeah, so yeah, okay. Syntactically, okay, I didn't explain it syntactically. So what will happen is this, it has two arguments. First is the address of the variable which is used for the checking, and second is some value or some again variable. So uh, uh, the value which is stored at this address is compared with this value, and if this is this one is lesser than this, like here, if this value is lesser than this, then this the value which is stored at this address location is updated by this value. So I hope that is clear. Exactly this functionality is being implemented by the atomic. Checking it,
Ye-
yeah, please go
Yes, I
ahead.
got it.
Yeah, okay, so checking it and then updating it. I hope that is clear. And again, if there are any questions, sorry, there is some question. Sir, could it be possible that all dist value for an iteration changes before the atomic mean starts? Okay, even if that is the case, then there won't be an issue, right? If let us come to Gokul's suggestion. What he was suggesting is, could it be possible that all dist value for an iteration changes before the atomic mean starts? So let us consider this scenario that uh, okay, but please note that this alt dist is a local variable. So for a particular thread, this value won't change, right? Because if it would have been a global variable, then some another thread might have changed this value of alternate distance. But since it's a thread local variable. Please note that whatever we declared inside, whatever we declare inside a kernel, let's say we declared int a, then that a is local to that thread, and no other thread will be able to see the value, see or update the value which is there inside that variable. Similar manner here, alt distance is a thread local variable. So no other thread apart from the thread which is executing this block or this kernel will be able to update the alt distance. So I hope that is clear, that no other thread will be able to update it, and hence it won't happen that some another thread might update the alt distance, and it might lead, I mean, there is no chance that it might lead to some uncertain behavior because of, I mean, the reason is that this won't be updated. I hope that is clear. Okay, so the short answer is that it is the thread local variable, and hence uh, there is no chance that it might be updated by other threads. Yeah, but if I missed something, then you can unmute yourself and ask Google. Okay, I guess things are okay. So let's move on further. Yeah, so we saw the write code for the single source shortest path. Now let us begin with the atomic CAS. So atomic CAS is again one type of atomic instruction, and its syntax is very simple. Uh, First of all, we need this. We need to understand this atomic CAS function. It has three arguments. First is the address, address of the, address from where we need to check some particular value. So, first argument is the address. Second argument is the value with which comparison is to be made. So the value which is stored at this address, which is provided as first argument, will be compared with the value which is mentioned as the second argument, or the value of the variable which is mentioned here. And if both matches, so value which is at this address matches with the value of this variable x, then if that happens, then the value of that value which is present at this address location is replaced by the value of y. So again, if this and this matches, then the value which is present at this address location will be replaced by the value of y. So I hope that's clear. And yeah, and it also returns something, and what it returns is the old value of the old value which is stored at this address location. So I hope that is clear. In case there are any questions, then please ask or put them in the chat. And talking about this atomic CAS, there are two typical use cases for this atomic CAS. One is for implementing the locks, and okay, so locks can be used for implementing the critical sections. And second application is in the implementation of single. There is something called a single section. And what is this? The single section ensures that only one thread, it can be any of the thread, but only one thread will execute a particular block. And all the rest of the threads won't execute that piece of code or that block, and they can move on further. But only one thread will be executing that piece of code, and yeah, rest can move further. That is the meaning of single section. So this atomic CAS can be used for implementing both of the things. And yeah, before moving further, let me quickly see if there are any questions. Yeah, there is probably one question. So could it be possible? Okay, yeah, this one I already took. Uh, okay, so any questions on the atomic CAS part or its syntax, or if anything is unclear related to atomic CAS, please ask them, or else we'll move further. Okay, looks like there are no questions. Then let's move further. Okay, so now let us start with a small class work. Let us say that we need to implement lock using the atomic CAS. How can we implement that? Okay, so let us start looking step by step. So let us start our class work. So let us say that I have this lock var, which is some variable, and since we need to pass address of it, I'm passing the address of it using ampersand lock var. So this will pass the address of it, and please note that this lock var is initialized to 0, and as a second and third argument I'm passing 0 and 1. So based on our previous slide and based on our understanding of this or working of this atomic CAS that we understood, Will this thing work? Can this thing or this single statement be used for implementing the critical section? Or, or let me put it in different way. Can this statement alone be used as a locking mechanism that thread might invoke before entering the critical section? And yeah, should this statement alone ensure that critical section will be implemented properly? Or in other words, will this work? I hope that question is clear. I request each and every one of you to think about it. Will this work? Uh, so critical section is after this. So each thread will execute this statement and will try to enter the critical section. And as we want mutual exclusion to hold, only one thread should enter the critical section. So will this statement be suffice, or will this statement ensure that the critical section is implemented? Mutual exclusion is ensured is the question. Please think about it. I'll wait here for a few seconds. Some suggestion: if lock variable is shared, then won't suffice. Yeah, lock variable is shared across all the threads actually. Request also others to try so that we can get the maximum out of this exercise. So lock var is shared, and as per the Rishikesh's suggestion, it won't be suffice. Any other suggestions apart from that? Let me quickly. Okay, looks like there are no suggestions. In anyways, let's move ahead. Uh, so again, this won't be suffice. So let us understand why it won't be suffice. Because it doesn't ensures mutual exclusion. So let us assume that even if the lock variable is initialized to 0, even if that is the case, then what this instruction does, it checks that is the value at this address equals to this value. Yes, it is 0, right? Value of lock var is 0, so 0 is equals to 0. So for one of the threads, since this thing is executed atomically, this is an atomic instruction, this comparing and then setting is done atomically. So for one of the thread, since initial value of lock var is 0, for one of the thread, value of lock var will be equals to 0. And for that thread, what it will do, it will set the value of lock var to 1, and then it will move on. And for rest of the threads, they'll check if value of lock var is equals to 0, but it's not the case, right? 1 is not equals to 0, so they'll do nothing, and they'll also move on. So important point to note here is that atomic CAS or any of the atomic instruction are non-blocking. So it won't happen that if lock var is not equals to this value, then the then particular thread will start looping here, or like that we had in case of while loop, right? While loop, right? So when the while loop was, condition inside the while loop was not getting satisfied, the thread was just looping over there. But here the atomics are non-blocking. So even if the value of the lock var is not matching with the value of the second argument, what will happen is they'll not set the value of lock var to this third argument, or the third value in the third argument, and they'll move on. So it will happen that multiple threads will enter into the critical section. So the mutual exclusion is not ensured. Okay, so we understood that this doesn't work because it doesn't ensure mutual exclusion, then how about this? We do this thing that we place this atomic gas inside a, what I can say is, we place this atomic gas inside if condition, and what we do is we check if the value returned by the atomic gas is equals to 0 or not. If it is 0, then execute the critical section. Will this work? Again, one thing that I want to clarify here is that the atomic gas returns the old value. So whatever the value, whatever was the value inside this uh, this var, or at this address location, is returned, and yeah, that is stored in the that is stored as the return value. So here the value that is returned is being checked whether it is 0 or not, and if it is 0, we'll execute the critical section. Again, will this thing work, or is there any issue with this? Would like to pause here for some time for you people to think. Please try out and post your answers in the chat. Okay. Probably I'll wait here. Yeah, please try out. And if you have any questions, then also you can unmute yourself and ask or type them in chat. Okay. Okay. There is some suggestion I can see. Would work for odd threads. Gokul, would you like to explain why it should work for the odd threads? I'm back to the slide. And can you explain why it will only work for the odd threads?
Oh, sorry, sir, that was wrong. It will
Okay.
work as long as the lockvar value isn't changed.
Okay, that is not an issue. I mean, committing mistakes is not a problem, but it is important to try again. I would like to highlight that trying is important. Making mistakes is okay. Uh, this would also have same problem. Would you like to put some light on why um, it would have the same problem, Rishikesh?
Sir, like for one thread, let's say it implements that statement, then it would return 0 and then it will go inside that if block.
Okay.
But
Yes.
for others, the lock var would be 1. So it would return, like initially it will be 1. So it will return 1, the atomic gas. And 1 won't be equal to 0, so it will not enter the block.
Yes. Yes. So I think that is the precise thing that Rishikesh suggested. So let us understand the issue here. So first of all, what is critical section? Critical section is a piece of code that should be executed by each and every thread, but one at a time. And the crucial point here to note about the definition of critical section is it should be executed by each and every thread. It should not happen that only one thread executes the critical section and all other threads just move further and they don't execute it. And that is what exactly is the issue that is happening here. The lock var initially set to 0, and for one of the thread who will see the lock var as 0, we'll see that okay, 0 is matching with 0, so I'll replace it by 1 and return the old value which was 0. So 0 equals to 0 will be true here, and it will enter the critical section. Okay, so far that is fine. You only want one thread to enter the critical section, but what will happen with the other threads? They'll come, they'll see that lock var is 1 and 1 is not equals to 0. So they'll do nothing because they'll not set, since this itself is not matching, these both values are not matching, they'll return the old value which is 1 and 1 is not equals to 0. So they'll not at all enter into the critical section, and they'll move further and start executing the instructions which are after that critical section, and this should not happen. uh, as I told, the definition of critical section is that each and every thread should enter the critical section in, I mean, they should enter critical section one at a time, and that is what we are not ensuring. What we are not ensuring is that thread should enter the critical section. But here what is happening is that only one thread is entering the critical section, rest all are just ignoring the critical section. And this should not happen. And that is the issue with this part. Okay, yeah, so precisely, precisely suggesting it does not block other threads. Other threads should wait here for the one thread to finish the critical section, and once that thread finishes, other threads should enter the critical section and start executing. So it does not block other threads, and that is the issue with it. So what about this? Again, making the above block. So let us say that we modified this block like this. So we now have this do while loop, and what we do is we again use atomicCAS, and again second and third argument is 0 and 1, and yeah, so we check the old value, and if it is not 0, then this while loop terminate. Sorry, if it is not 0, we'll keep on looping, and if it is 0, then this while loop will do while loop will terminate, and we'll move to the critical section. Again, my question is simple: will this work? Will this thing work? Or in other words, will this thing ensure the mutual exclusion? I hope that the question is clear. Okay, I'll switch back to this slide so that people can clear. Let me switch back to the channel. There is some suggestion. As long as we reset the lock variable, it should work. Okay, Gokul is saying that it should work, and yeah, and yeah, that is correct observation. That once this thing, one of the thread finishes this, and they enter the it enters the critical section, and it finishes the execution of the critical section. We should reset the value of lock variable uh, to 0. And yes, that is correct observation. So yeah, I think this is the correct observation as well as the answer. Request others also to try, but yeah, meanwhile we'll move further with this. Yeah, so uh, this this will work probably. I won't say that 100% it will work, but we'll come to it. But yeah, this code can work. And why it, let us analyze why it should work. Because let us see how, what will be the execution pattern. So let us say that there were multiple threads who were executing and who were willing to enter into the critical section. And yeah, so lock_var was initially 0. So one of the thread will see the lock value as lock_var as 0. Will compare 0 with 0 and will set it to 1. And yeah, since the old value of lock_var was 0, old will have 0, and 0 is not equals to 0, so it will enter the critical section. That is fine. And we need to also check if other threads are blocked here, because one of the thread have already entered the critical section. So since it is inside the critical section, it is important to block other threads, right? So since lock_var is 1 now, all other threads that will be entering into this do while loop, what they'll see is lock_var is 1 and this is 0, so 1 is not equals to 0. So they'll get old value as this 1, and 1 is not equals to 0. So they'll keep on looping here. That is fine. They'll keep on looping here, and The thread that entered critical section will finish the execution of critical section, and it will reset the value of blockvar as 0. So again, since blockvar is set to 0, one of the thread will succeed in checking 0 equals to 0 and setting it to 1, and then since old value will be 0, one of the thread will enter another, the one that apart from the thread which entered into the critical section, apart from that thread, some another thread will be entering into the critical section. So yeah, the observation here is that if you use this code, then mutual exclusion is guaranteed in some sense. But there is also some issue with this code, but we'll see this later. But okay, let us keep that issue aside for a moment. But I have one more question here. Let us say that our requirement is slightly different, and we want to just don't want. We want something else. So we also want that okay. We here also wanted to know that which thread have entered into the critical section, and in order to know that, we need to modify this code somehow. And I would like you people to think that. Let us say that our requirement is such that along with mutual exclusion, we wanted to know which thread has entered into the critical section. If that is the case, then how will we modify this code so that we can keep track of which thread has entered the critical section? Please note that any of the thread can execute atomicCAS and can enter the critical section. So yeah, so please think about it, that how can we keep track of that thing, that which thread has entered the critical section? Is there any way, is there anything that we can do here? Okay, switching back to the slides so that you people can try. I'll wait here for a few seconds. I hope that question is clear. We just don't want, along with ensuring that the mutual exclusion is followed, we also want to know which thread has entered the critical section. So that is the question. And how can we do that? How will we modify this code?
Excuse me, sir.
Yes.
Sir, I joined later. So I asking one question, that is, in case of atomicCAS, so whether after execution of the critical section automatically logvar will be set, will be reset. So it will be done automatically.
No. So resetting, we have to do it explicitly. So this is one piece of code which implements some sort of lock, and for unlock we need to set lockvar equals to 0 explicitly. So reset is not an
Okay, sir.
Yeah.
Okay, sir.
Yeah, that is. There is some suggestion. Okay, there are some suggestions. Replace one with thread ID x dot x. Okay, this is a valid suggestion, but there is a small corner case here, Gokul. What if the thread ID is 0? It might be the case that thread has ID 0, right? In that case, what will happen? So if thread has ID 0, then replacing 1 by thread ID x, what will happen? If we okay, I'll repeat this. If 1 is replaced by thread ID x dot x, and if the thread ID is 0, then what will happen? Lockvar will get the value 0, and this should not happen, right? Because if that is the case, more than one thread will enter the critical section. So your thinking is in the right track, but needs some refinement, what I would say. We can have a shared array and set the value at index thread id x dot x as 1. Have a shared array and set the value at index thread. Okay, that is fine. But that is quite an overhead, right? I would say, Rishikesh, that we'll need to have the entire array, and we need to set and reset that array and access those elements of the array. But we can do something very cheap rather than declaring this entire array. We'll see probably. Would that replace lockvar with thread ID and send the value back to us? Yeah, that is correct. It will send us a thread ID back. Your observation is correct, but there is a corner case here, right? That when thread ID is 0, what will happen? More than one thread, two threads will enter in the critical section at that time, right? And that is the issue. Only one thread should enter into the critical section at a particular time. Okay, so solution is simple. I'm just building up on the Gokul's suggestion. Okay, so there is some other suggestion. We can have only one shared variable and equate it to thread ID. Yeah, again, yeah, this can also be done. Yeah, but again, coming to your suggestion, Rishikesh, there might be data race while writing also. So you need to take care of where are you setting that thread ID x.x, because it might happen that multiple threads might want to write into that shared variable, and at the end it might happen that the thread which is entering into the critical section might not be the one who is, sorry, the value that is set into that variable, shared variable, might be different than the thread which is actually entering into the critical section because of data race. I hope you are getting that point. But you can again rethink over that approach and refine it a bit so that uh, yeah, that is correct. You can check old equals to thread ID x, but will it ensure that only one thread will enter into the critical section? Is the question. We are replacing it with, we are replacing condition with thread ID x dot x. Okay, I think it should work, but I need to check this one. Gokul, I need to check your suggestion if this works. But yeah, most probably it should work if we add this into the condition, while condition. I think it should work, but I'm not able to see any issue right now with this. But okay, so let us see what what I was thinking was slightly different. So what we can do is instead of doing this thing, we can do it in slightly different manner. Let us say that we know the upper bound on the number of threads. Let us say that we know that thread uh, number of threads with which the kernel is launched doesn't exceed some 1 million, right? So in that case, what we can do is we can set lockvar to int max, and then after doing that, what we can do is we can check if the lockvar is int max, and if that is the case, if both of them matches, then what we can do is we can replace this one. We should replace this one by the thread ID x.x in the same way that Gokul was suggesting. So advantage with that thing is that we won't need to do this thing. We won't be having the data race for the case where thread ID is 0. Yeah, so because since we have upper bound on the number of threads, that we won't have more than million threads is what our assumption is. So none of the thread will have ID equals to int max, right? And if that is the case, only one thread will enter into the critical section, and yeah, so mutual exclusion is ensured, and the value of the lock wire will be the thread ID, which will be which will be entering into the critical section. So I hope you are getting it. We'll set lock wire to int max. Here instead of 0 we'll have int max, and here instead of 1 we'll have thread ID x.x. Any questions up till this point? Okay, I think that there are no questions. In that case, let us move further with our discussion. Okay, so I told that this code is correct, right? But there is one small catch with it. There is one small caveat with this code still, that this code works on the CPU as well as it works on the GPU across multiple different warps. But there is a small issue with respect to the threads of the same warp. So what will happen when we execute such kind of code? for the threads of the same warp, what will happen? As we know that warp threads execute in SIMD manner, uh, what will happen is that let us understand what will happen. So all the 32 threads, that is all the threads of the thread of the warp, will start executing this as they execute in lockstep manner. They'll start executing this do while loop. They'll start executing this atomicCAS. They'll see that only one thread succeeds in the sense getting the old value as 0. So only one thread will get the old value as 0, because for only one thread lock var will be equal to 0, and that thread will set lock var as 1, and will get old value as value of old as 0. And for rest of all the warp threads, what will happen is, since lock var is 1, 1 is not equals to 0, and lock var will stay 1, and the value of old will also be 1 for them. So now what will happen? Only one thread of the entire warp has old value as 0. So for that thread, this this old not equals to 0 condition is false, because 0 not equals to 0 is false. So it tries to move to the it will proceed moving towards its critical section. But for all other threads of the warp, 1 is not equals to 0, which is true. So they all can't enter into the critical section, and they'll keep on looping here, right? But since, as we know, that warp threads execute in SIMD manner, so that one thread which wanted to enter into the critical section will also be not allowed to enter the critical section, because of that SIMD sort of execution by the warp thread. So that one thread wants to enter the critical section, but because of the SIMD execution pattern of warp threads, it has to wait for the other warp threads which are looping here. And what this other warp threads are waiting for? It is waiting for that thread which has to enter into the critical section to reset the value of lock var. But that will not happen, right? Because that thread is waiting for the other warp thread. So here, if you see, there is a kind of a deadlock situation. One thread is waiting for other threads, and other threads are waiting for that one thread. So this is a deadlock situation. And yeah, so important point here to note that this code will work, but only on the CPU and across the across the warp threads of the GPU. But for the same for the threads of the same warp, this code will lead to deadlock. And yeah, precisely speaking, this code will work only in case of MIMD execution, or multiple instruction multiple data sort of execution pattern. For SIMD pattern of execution, like for warp threads, it will fail, or it will lead to deadlock. Okay, so yeah, the point is simple. It will hang for threads belonging to the same warp. And why? Because when one warp thread acquires the lock, it waits for other warp threads to reach the instruction just after the do while loop, and other warp threads await this successful thread in the do while loop. So yeah, I hope that you are getting this, that this other threads are waiting for that one thread is waiting for other threads. Any questions up till this point? Else, yeah, please.
Sir, we could do that where we allow like the whole warp to go through the do while loop, and then we can use that if statement atomicCAS that we saw, sir, to allow only one thing to execute.
Okay, so you are suggesting that will entire warp. You are suggesting that entire warp can execute. Go into the critical section, and then what? I missed that part. Entire
And
warp
then
is,
we saw
yeah.
like an earlier like if statement with atomicCAS, no, sir, that all other threads will go past and only the one thread will go in. But then okay, then those threads might miss the critical section.
Yes, yeah. Your observation is correct. We can use that atomicCAS if condition inside. Inside if we can use atomicCAS and restrict only one thread to enter, and that can solve this issue. But there is something else that we need to do for that to implement this atomic thing correctly, and we'll see this in next slide. But yeah, your observation is almost correct, but still there is some small thing that is missing. But yeah, we'll see them. Any questions up till this point? If you have any questions, then please feel free to ask them. So, yeah, some suggestion. Yeah, we can use negatives. Yes, we can use negatives instead of int max also, because thread ID won't be negative. So yeah, negative is also one possible way in which we can do that. But yeah, I mean, when I thought about it, I thought in terms of int max. So yeah, I mean, generally int max is a very large number, and the number of threads with which we launch the kernel is, I mean, it's in typical applications, it is generally lesser than int max, so we can use that thing. But yeah, you can also use negatives instead of int max. Yes. Yeah, so I hope that is clear. Apart from that, any questions? Okay. Just a moment. Yeah. So yeah, let us move further if there are no questions. So we understood that this thing, which is uh, this do while loop, then entering into the critical section and then setting lockvar to 0. Please note that this statement is setting lockvar to 0. It is just that this is overlapping with it. But yeah, here we are setting lockvar to 0. So this thing, this locking here, then entering critical section and then unlocking, works on CPU as well as the uh, as well as between the different warp threads of sorry, as well as the threads which are within the different warp on GPU. But for warp thread, this thing leads to deadlock. So how can we solve this issue? Can we modify this code in some way so that it also starts, I mean, it also works for the threads within the same warp? Please note that it should work for the threads within the same warp as well as across the warps and thread blocks and so on. So it should not happen that when you try to fix this issue, that is within warp thread should not lead to deadlock, the other threads start showing some issue. So it should not happen. It should be working for all the threads on the GPU. Please think about it. Please try, and if you are not able to get it, then we'll see it. But yeah, please try it so that you can get some idea about how can we implement locks on the GPU, or the critical sections on the GPU. Again, I'll be switching back to this slide so that okay, I'm unable to see any suggestions. Anyways, since we are running out of time, let me quickly move to the solution. So on GPU, what we can do is instead of okay, on GPU, what we can do is instead of doing this thing, what we can do is we can use one if condition here. So let us see how the execution pattern is here now. So we are replacing this, yeah, this thing is same. First of all, please note that this thing is same. So only one of the thread will be getting the old value as 0. Rest all will be getting old value as 1. Since this atomicCAS is atomic, only one thread will get old value as 0. And that thread will enter into the critical section, because if old is 0, uh, and please note that this old value is only 0 for one thread, so that thread will enter the critical section. All other thread will be masked out at this moment, because as you people might be remembering from our thread divergence discussion, that this condition is only true for one thread. Rest all for rest all threads, this condition is false, so rest all threads will be masked out. That one thread will enter into the critical section, will finish the execution of critical section, will then do lock var equals to 0, and then what it will do is it will come out. It will come out of this if condition, and then what it will check is it will check if old value is not equals to 0. It will check this exactly this thing. Please note that this condition and this condition here inside this while loop are same. This, sorry about this. This is an overlap here, but yeah, the condition here inside this while loop is same as this condition. So now, please note that out of all the 32 threads, only one thread was able to enter the critical section. In fact, inside this if condition, was able to enter the critical section and execute it and set lock var to 0. Rest 31 threads were here doing no op. Now, after this if condition is finished, execution of this if block is finished, what they'll do, all the 32 threads of the bot will start executing this while statement. And since old value is 0 for only one thread which executed this critical section, only that thread can come out of this while loop, because for only that thread 0, which is value of old, is not equals to 0, is false. So it will come out and will wait here somewhere for other threads to also come. But for other threads, old, which is 1, is not equals to 0. So this while condition is true. So they'll again they'll again execute next iteration of do while, and they'll start executing this block again. So please note that one thread has finished. It is waiting here for other because they are var threads. So it has to wait for other 31 threads. Now this 31 threads will again be competing for the block where getting old value as 0 using block where. So again, only one thread will win this competition because it's an atomic operation. So out of the 31 thread, again only one thread will get old value as 0. That thread which got old value as 0 will enter the critical section and will reset lock var to 0. Meanwhile, all 30 threads were here executing no op, and once that is finished, that one thread will be exiting this while loop, and rest 30 threads will again loop again, and so on. So execution pattern will be like this. Initially one thread will succeed, rest 31 thread will loop again, then second thread will succeed, all 31 threads will loop again, third thread will succeed, third thread will succeed, rest 29 threads will loop again, and so on. So once all the warp threads have finished this while loop or the iterations of the while loop, then all 32 threads will be here, and then only once they reach, all of them reach here, then only they can move ahead because of that SIMD execution pattern. So I hope this is clear. If there are any confusion or questions at this point, then please feel free to ask. This is a very important thing to understand, since this is the way in which we can implement critical section inside the GPU. So if there are any question or any simple confusion also, then please ask here. Okay, there is some suggestion or question. We could select a work to send. Yes, we could select a work to send through and loop over an if condition 32 times, changing if condition slightly every time. Okay, I was unable to understand this thing, Gokul, but if you want, you can explain this thing in detail. I'm unable to understand this properly. Threads to send through then loop over if condition. Okay, if you feel that this thing can work, then you can try writing a code corresponding to it.
Sir, similar idea only, sir.
Okay. But I was unable to get that. Okay, anyways, yeah, so this code will work for all the warp threads, within the warp threads as well as the threads within the different warps and the different thread blocks and so on. So I hope that you are clear with this. So with this, let's move on further. So now let us try a simpler problem. We want to implement single with atomicCAS. So what is single? Single is a block of code that should be only executed by one thread, and other threads, that thread can be arbitrary. The one that is executing that block of code can be the thread which is executing that block of code can be any thread, and all other threads need not wait for that thread to finish that block of code. They can move further. So we want to implement that functionality using atomicCAS, and please think about how can we implement it using atomicCAS. I think this should be easier for you to easier for you people to implement now after this discussion. Yeah, please try out. After the discussion of this lock, it will be way too easier for you people to implement this single single using atomicCAS. Please try out, and meanwhile, if you have any questions or any suggestions, then post on chat, or you can unmute yourself and ask. If statement like we saw earlier, can you quickly type in chat? How can we do it, Gokul? If there is some suggestions, we can put just one if statement and put the critical section inside the setting block where it's not. Okay. I think I think both of you are close to it. I think this this approach is also correct. We can just put one if statement and put the critical section inside the resetting lock variable is configured. Yeah, I think this will work, and Gokul's suggestion is also correct. Yeah, send some okay, lock where then -1. Okay. Okay, lockvar comma -1. So you should initially set lockvar as -1, else no one will be able to enter, right? Yeah, but I still think that there might be some issue with this. Lockvar is -1, then -1 equals to -1, and some thread ID. Okay, I think this should work. I think it will work, assuming that lockvar is initially -1, because only one thread will succeed in checking succeed in that check where lockvar is -1 and it is compared with this second argument. So that thread who succeed will set lockvar to its thread ID, and since thread IDs are unique, only one thread will enter into the that section or the single section. So okay, I think both of these suggestions are correct. Yeah, but let us see how can we do this. So yeah, typically it can be done like this. So assuming that this lockvar is initially set to 0, and we pass this address of lockvar as first argument, and what we do is the second and third argument are again 0 and 1. What we do is multiple threads are executing this instruction before this atomicCAS. The first thread to succeed at this atomicCAS, or the first thread which will check this lockvar and compare it with 0 and will get and will succeed in this check and will set lockvar to 1, will get the return value as 0, right? And it will also succeed in this checking, right, if condition, that is 0 equals to 0. So that thread will enter into the single section, and since it has set the lockvar as 1, what will happen with the other threads? Other threads will not be able to enter into this single section, right? Because for them lockvar is 1 and 1 is not equals to 0. So the value returned here by atomicCAS will be 1, and 1 is not equals to 0 again. So they won't be entering the single section, and what they'll do, they'll just move on, right? They won't wait here for the thread which is executing the single section, and they'll move on, and that is what exactly we want, right? Only one thread will be entering the single section and is finishing that section, and all other threads which didn't succeed at here, they moved up. and yeah, executing the instruction which are after the single section. And yeah, so this is the one of the way in which you can implement. Yeah, I mean there are multiple ways, but this is one of the way. And important point here to note that it is okay if we don't set lock wire to 0 at the end of the single section, because yeah, I mean it won't lead to any issues with our the way we want the single section to be. I mean, it doesn't cause any issue with the functionality of the single section, even if the lock wire is not set to 0 at the end of the single section. I hope that is clear. If there are any questions, okay, Gokul is saying, but we have to handle warps. Is it related to this thing, Gokul? I think it will also work for warps also, I think. I don't think that there will be any issue with the warp, because let's say there are multiple warp threads, then only one warp thread will succeed here, and rest all warp threads will move on, and that warp thread which succeed with this atomic gas, that is getting the return value as 0, will enter the single section, and rest all warp threads will wait for that. Yeah, rest all warp threads will wait here uh, while this single section is being executed by the uh, that single thread which is part of that warp. So all other warp threads are waiting here. Meanwhile, that one thread which succeeded here of that warp is executing the single section. Once it finishes, uh, once that thread finishes, it will exit this single section, and it will join that all other 31 threads which are waiting here for that thread, and then they'll move on. So I don't think that there is any issue with uh, the warp thread in case of this implementation of single. But still, if you have any questions, then you can ask. Okay. Ukul is saying yes, sir. Okay. I hope that it is clear that there won't be any issue with the warp threads for this implementation of signal. If there are any further questions, or if you feel that I missed something, then you can unmute yourself and ask. Okay, so let's move ahead. So I want you people to think about what will be the output of this code, uh, or what are the possible outputs uh, that can generate out of this code. I'll wait for a few seconds here so that you people can try. Yeah, please think about it. What can be the output with this code, and please post your answers in the chat, or you can unmute yourself and ask, or uh, you can unmute yourself and tell your suggestions related to that. I am hoping that you people are trying. So I'll wait here for few more seconds. Please try out, and even if the answer is incorrect, that's okay. But please try out so that we can learn. Yeah. Okay, since there are no suggestions and since we are running out of time also, let us try to understand this code and let us see what can or what are the possible outputs with this code. So initially we are declaring this integer pointer and we are allocating the memory using CUDA malloc on the GPU of the size of the size of single integer, and that allocated memory on GPU which is which is used for storing exactly one integer is now being pointed by GG, which is pointer on CPU. It is pointing to some memory location on GPU. Then we are doing this CUDA memset, which is some new function, and it's very intuitive. CUDA memset is used for setting some memory location on GPU. So here we have this integer declared on GPU, right? So we are setting its value to 0. Then we are launching kernel with two blocks, two thread blocks, each having 32 threads or each with one warp. So two blocks with each with one warp. We are launching the kernel and we are passing this GG, which is which is the integer declared on the GPU memory. Then what we are doing is we are using this atomicCAS, and we are checking if the value of GG is 0. So one of the thread will succeed here, right? Out of all the 64 threads, please note that this kernel is launched with 64 threads. So exactly one thread will succeed with this check of GG equals to 0. So one thread out of that 64 thread will succeed in this check, which is GG equals to 0, and it will set value of GG to thread ID x dot x plus 1. That is its ID plus 1. So it can be any of the thread, right? It can be thread 0 or thread 1 or thread 5 or thread 10 or thread 31 of any of the block. Please note that there are two blocks, and out of threads of any of the block, please note that we are not using any block ID here. So block ID is not coming in picture. So it can be thread 0, 1 or any of the thread from 0 to 31, having thread ID from 0 to 31 of block 1 or block 0. So one thread out of out of any of these two blocks will succeed in this check and will set value of GG to thread ID x plus thread ID x dot x plus 1. Okay, since this atomicCAS will be success and will get old value as 0, this printf will be done definitely. This printf will definitely occur. And what it will print? It will print the thread %d, which is the thread which succeeded here. Not thread which succeeded here, but the value, the thread succeeded here in executing this atomicCAS. It will print the thread ID of that thread, and thread with that ID succeeded, which is, and then 1 will be printed, and then again we are doing atomicCAS. And what this atomicCAS is doing, it is checking value of GG with 0. Now please note that when this atomicCAS succeeded for any of the thread, even if it's a thread 0, it is replaced with thread ID x dot x plus 1, and since thread ID cannot be negative or less than 0, thread ID x dot x plus 1 will always be a number which is greater than 0, and if that is the case, GG won't be equals to 0, and if that is the case, this atomicCAS, this comparison will not succeed in this atomicCAS, and if that is the case, the value of GG won't be replaced with this part by any of the thread out of the 64 thread. Hence, this second printf, no matter which thread it is, it won't be printed in any of the case. And and again we come to this third atomicCAS, and in this third atomicCAS we are comparing GG with thread ID x dot x. Now let us understand which thread will succeed here. So thread which set this GG value to thread ID x dot x plus 1, the thread which is its successor, or not successor, but the thread which is having ID just 1 greater than it will succeed in this atomicCAS, right? Because the value of GG will be thread ID x dot x plus 1, and let's say that thread ID x dot x was 1, then the thread which will succeed here will be thread 2, because value of GG would be set to 1 plus 1, which is 2. So 2 is equals to thread ID x dot x, and this will be, this check will succeed only for thread 2, because GG is 2. And if that happens, then GG value is set to -1, and old value that is written is, well, it's 1. No, wait, it won't be 1. Yeah, sorry, it will be 2, because that was the value inside the GG. Now it is set to -1, but yeah, initially it was 2. So old value that will be written is 2, assuming that the thread 1 succeeded with this atomic CAS. Then thread 2 will succeed with this atomic CAS, and then it will answer, and then it will enter inside this if condition, because old is 2, thread ID is 2, and it will print this thing. Now, one more question. Will it happen that this printf is always executed? Well, that thing is also not guaranteed, because let us assume that the last thread of a warp, last thread of the warp, it might be either of the warp from block 1 or block 2. But let us assume that last thread of either of the block succeeded, or last thread of either of the warp inside this both of the blocks succeeded. In that case, thread ID, value of GG will be set to thread ID x dot x plus 1, which is 31 plus 1, since ID go from 0 to 31. Thread ID, GG will be set to 31 plus 1, which is 32. And no thread will have ID 32 here. So GG is 32 here, and no thread will have ID 32. So if that happens, then no thread will enter here in this condition. So again, two cases. Thread from 0 to 30, thread having ID 0 to 30 succeeds with this atomic CAS, any of the thread out of that 0 to 30. If that is the case, then this will be executed, this if, and then this if. And if that is not the case, that is the last thread succeeds here, that is thread 31, then this if will succeed, but this printf will not be executed, since thread GG will have 32 and no thread ID will be 32. Thread ID x dot x will be 32. So this can be printed, then this, or alone this will be printed based on who is executing this atomic CAS. I hope that is clear. If there are any questions here, please feel free to ask. Yeah.
So the atomic CAS will return the y value or the return value?
Sorry, can you repeat? I missed some of your words.
The atomic CAS will return the y value also for this.
Yes, it will return this. No, it will not return y value. It will return the old value which was there in GG. Okay, so please let us clarify this thing. So it will return whatever is old value in this var. It will return. It is what is old value. It will never return this y value. It might return x value if this both are matching. Var and x are matching, then it might return the x value, because that is the old value in the var. But it will never happen that it's returning y value, unless it is the case where x and y are matching and the value of y is equals to x. I hope that is clear.
Okay.
Yeah, so to keep it simple, it returns the old value which is there in this first argument. Okay, any further confusions here? If there are any, please ask, otherwise we'll move further. Okay, I see that there are no questions. Okay, then let's move further. We have few minutes more. Okay, so as I explained, 64 threads, kernel is launched with 64 threads, and some threads out of the 64 threads, some thread out of 64 updates GG2 thread ID plus 1 here. So one of the thread out of the 64 thread updates this GG2 thread ID plus 1. Then warp threads do not execute atomic together. Yeah, please note that even warp threads don't execute atomic instructions together. Even they execute instantly, they'll also be serialized for executing the atomics, like this atomic CAS. So that is also done sequentially or serially. And irrespective of which thread executes the atomic CAS, first atomic CAS, which is this, no thread would be seeing GG value will be seeing GG value as 0 because it is set to thread ID x dot x plus 1. Hence, the second printf will never execute as we discussed. And if any of the threads any of the threads having ID from 0 to 30 executes this atomicCAS, then the threads having ID from 1 to 31 will be succeeding here, and based on what thread is succeeding here, that thread, the ID of that thread plus 1 will be succeeding here, and it will set GG value to -1, and then it will execute this if condition, enter into this if condition and print this statement. And if it's the last thread of that work, then this condition would this print won't happen. And yeah, so that is written here. Otherwise no one would update GG to -1, and no one would print the third printf. That is what we saw, right? Yeah, so the most expected output, or the most probable output out of this when we execute this code is that you will see that thread 0 would execute the first printf, which is this here. Thread 0 will print this first printf, and then thread 1 will succeed in printing this third printf. So that is the most probable, but please note that this is the most probable output. It doesn't mean that the other outputs are not possible. So I hope this is clear. Okay, I can see that there are no other questions. So if that is the case, then let's move on further. So till now we saw this control plus data flow, and we also saw multiple things related to atomics, right? We saw how to use different type of atomic instructions like atomicMin, atomic increment, atomicCAS, and in the same way we saw how to use atomicMin. We can also use same syntax but in a slightly different manner, or syntax is same, but we can use the different atomic function, which is atomicMax, and it's very similar to atomicMin. It takes 2 argument, and but its functionality is different. It instead of checking for minimum, it checks for maximum. So that's only the change. So yeah, we saw multiple atomic instructions, which is atomicMin, max, increment, atomicCAS, and yeah, with this we ended with the atomics, and now let's let's start with the barrier. So yeah, so let us start with the barrier. Probably let me see how much time we have. Okay, so we have few minutes. So yeah, let us start with this. Probably we'll cover this slide and then we'll stop. So okay, so what are the barriers? So probably we have seen this barrier before during the memory lectures where we were using that sync thread. So that is one sort of a barrier. And what this barrier does, it is so first of all, what is barrier? So it is a synchronization point or a program point where all threads need to reach before any of the thread can proceed further. So let us come back to the analogy that I gave during the memory lecture also for sync thread. So let us say that we all of us decided to go to football ground for playing the football. In that case, what we will do, we'll move in asynchronously from our houses to some common point where we'll meet, right? So we'll asynchronously, or in different we'll asynchronously move from our houses, and we'll try to reach at that common point or that common ground, and after reaching that common ground, we'll together move towards the football ground for playing the football. So that reaching that common place is the synchronization point. So we move at different speeds from our home to reach that common point, and that is what is asynchronous execution. We are moving at different speeds to reach at that common place, but once all of us reach at that common ground, then only we'll move further to the football ground for playing the football. So that is sort of a that is what is sort of a synchronization point or barrier. And yeah, so I hope that you people got it, that barrier is a program point where all threads need to reach before any other thread can proceed. And yeah, so this point is important. End of kernel is an implicit barrier for all the GPU threads. So kernel, statement which is after kernel will only, yeah, so not statement after the kernel, but the end of the kernel, or the place where kernel is finishing. All the thread, kernel will not end until all the threads have finished the execution of the kernel. And so, yeah, in some sense, we can say that end of the kernel is an implicit barrier for all the GPU threads. And yeah, so initially the global barrier, or the barrier across all the threads of the GPU, which is uh, the all the threads of all the thread blocks, was not supported. So we know that threads between the threads within the thread blocks, thread within the thread block can be synchronized using sync thread. But if you want to synchronize the thread which are across the thread block, then we haven't seen any synchronization construct for it so far, and it was also not supported few years back. But now it is supported using something called as grid.sync, and it is supported from CUDA 9 onwards. So this is quite powerful. It can be used to synchronize all the thread across all the thread blocks, as well as all the grids. So yeah, so sync thread is important, and it's kind of a global barrier now which is supported. And for the threads within the thread block, as we all know that it can be, they can be synchronized using something called a sync thread. And we saw this during the memory lectures. And yeah, one last thing, what about the barrier within the warp threads? How can we ensure that there is a barrier between the, within the warp threads? First question is, do we need the barrier within the warp threads? No, right? Because warp threads themselves execute in SIMD fashion. So only first instruction will be completed, and then only they'll move to the second. So in some sense, if you see, there is some implicit barrier for the warp threads. So yeah, so point here to note is that for warp threads, there is an implicit barrier, and we don't need any barrier for warp threads. Again, for warp threads, we don't need any barrier. For threads within the thread block, there is a barrier, and that barrier is sync thread, which we can use. And for threads across the thread block, there is now a synchronization construct which is called grid.sync is supported. And yeah, using this construct, we can synchronize the threads uh, which are within the different thread blocks. So I hope that is clear. Three things: warp, thread block, and multiple, threads of multiple thread blocks or a grid. So yeah, at all the three levels, we have now the support for adding the barriers. Okay, I'll probably stop here because we have uh, exceeded the time. But if there are any questions, I'll be there here for a few more minutes, probably 2 or 3 minutes more. And if there are no questions, then we'll call it a day and we'll disperse.